So a single water molecule down in the water column, down inside the water, is surrounded by water molecules. Are there forces of attraction between the water molecules? Or in the molecules of any liquid? Sure, there are. So this one has got forces of attraction out to all of these other molecules, evenly distributed, pulling it equally in all directions. What about a water molecule that's up here at the top? How is life different for this molecule versus that molecule? Okay, it's lonely. I mean, it's still got water molecules to most of the sides of it. What's the chief difference there?
It's flat.
Well, if we sort of pull these two out and imagine that one at the surface, that one down in the water, and we draw it a little bit bigger. This one has got forces of attraction running out in all directions evenly. This one that's at the surface does not. It lacks anything above it to direct force of attraction at. And as a result, the forces of attraction out to the sides, to those other water molecules that are also at the surface with it, are significantly stronger. They adhere together more tightly. The forces of attraction between them are actually stronger. That creates this sort of skin on the surface of the liquid. That's surface tension. That's why we can float a paperclip on water. The paperclip's obviously more dense, but we can catch it on the surface tension. If we puncture through, it will drop like a little, well. So this surface tension exists really only at the exact surface of the liquid. And it exists in all kinds of liquids. Water has got really high surface tension because of two things that we're about to talk about. So, wow, that's terrible. So cohesive forces are forces of attraction between molecules of a substance. So within a glass of water, within a pond, within something else, the water molecules are attracted to one another, and that's cohesion. Those are cohesive forces. We sometimes use the word cohesion like we could talk about a team being cohesive, or a marching band being cohesive, or a family being cohesive. It means that they stick together with sort of their own kind. The team sticks with the team. The marching band sticks with the marching band. The family sticks together. You know, you pick on my siblings, you're going to have to face me. That's cohesiveness. Okay, cohesiveness is largely what causes surface tension. Great. Water has got extraordinarily high cohesive bonds. Water has high cohesion. High surface tension. Good, okay, great. This makes water striders possible. There's one other force we want to talk about. We've got my little beaker of water here again, and there's something funny about the top. What is it?
It's square.
The top of the water surface.
It's curved in.
It's curved at the edges. It's got a very slight little curve there. I'll sort of overemphasize it for the purposes of talking about it. And when you've read your graduated cylinders, that curve exists. What's it called? Meniscus. The meniscus. Why do we get a meniscus? Why do we see a meniscus when we're reading water in a graduated cylinder? What causes that phenomena? Because water is attracted only two things in the world: itself and everything else, including the glass on the sides of the graduated cylinder. So the water molecules that are over in this section closest to the edge are attracted to and actually pull up along that glass as sort of more of them try to crowd over. Well, that's fine. Why doesn't it look like this? Because the little molecules that are trying to stick to the glass are pulling their friends along. Because water's only attracted to two things on the whole planet. Itself, everything else. We're kind of sick of that. So that enables water to do something very special. I've got a little capillary action, simply a result of the attraction of the surface of the liquid to the surface of the solid. And it's the same thing we see when water sort of balls up on a spoon or a cutting board or a counter or a piece of glass. We say it beads up.
Yeah, that's what I was looking for when I said bubbles.
Yes, I knew what you meant. So water beating up is just more evidence of capillary action. We haven't talked about equilibrium. We haven't talked about Le Chatelier's. Le Chatelier!
Chatelier's. Okay.
What did you just say?
Chatelier's.
Okay.
I didn't think so either.
What'd you think he said?
Something that sounds similar but is not. And that I would have to write him up for.
I didn't say that, but that.
Okay. Yeah, it's done. It's done. And yes, we all figured it out. So, equilibrium. Your notes say this is a dynamic condition. What does dynamic mean?
Yes.
Changing, not static. So if something is static, it's standing still. If something's dynamic, it's constantly changing. In which two opposing changes occur at equal rates in a closed system. So, give me an example of an opposing change. Two opposing things. Could be going back and forth. In chemistry. Okay, condensation, evaporation. What? We could have opposing forces, sure. We're going to talk. We can talk about equilibrium in terms of chemical reactions. And we can talk about a chemical reaction that goes both ways, a reversible reaction. But here, for our purposes, we're going to talk about it primarily in terms of state changes. So this is where we've got something changing states, but it's actually going back and forth. And I'm going to draw a closed system. So rather than the usual beaker we draw, this is a beaker with a plug in it. Okay? You have to imagine that that's a perfect plug. So nothing can enter that beaker or leave that beaker from outside. And inside that beaker, we have some liquid water. And above the surface of the liquid water, if we've pumped out all the other gases, all the other nitrogen and carbon dioxide and everything else, what are we going to have in a vapor phase? Some water. Yeah. So we're going to have molecules of water that are existing in a state where they are moving slowly enough that the forces of intermolecular attraction are holding them sort of in lockstep with one another. They flow past one another, they glide past one another, but they're constrained. They're in a liquid. And we're going to have some of those little molecules that are much freer. We'll do those a little bit bigger. That are up in the vapor phase. Now, if I have that system and it's sitting at temperature and it's been at the same temperature, and you can pick anything between 0 and 100. You know, it's sitting at 25 degrees Celsius. It's sitting at 55 degrees Celsius. Whatever. Are all the same molecules always in the gas phase and all the same molecules always in the water phase? No, they're not. We get little molecules of water that are in the gaseous phase that as they zip around, because they're moving pretty rapidly, hit the surface of the water. Well, what happens when they hit the surface of the water? They stick, because there are strong intermolecular forces of attraction between those water molecules. Well, we've got the little water molecules in here that are zipping around, and every now and then, one of them hits the surface. And guess what? If it has enough energy at the point when it hits the surface to overcome those bonds of attraction that are holding it down with all its friends, it's going to fly out into the gaseous phase. So we constantly have, every second, every nanosecond, some water molecules going from the liquid phase to the gaseous phase, and some water molecules going from the gaseous phase to the liquid phase. At equilibrium, the same number of particles are going each way at any given point. So if we have a total of, I'm going to make up some really silly numbers here. If we have a total of 1,000 water molecules, and at this temperature, 700 of them are in the liquid phase, and 300 are in the gas phase. What we're saying is that if this system is at equilibrium, they're going back and forth, but those numbers are going to stay constant over time as long as the system is at equilibrium. So they're going back and forth, they're trading places, but overall the system stays with roughly 700 in liquid, roughly 300 in gas. Let's try something. We have our liquid plus heat, and that yields vapor, and vapor, if you cool it, yields liquid plus heat. If we add heat, we're going to shift the equilibrium towards the vapor side. So where we had the 700, 300, we might end up with a 600, 400. Okay, now let's talk about cooling it a little bit more.